you very much. So this webinar is the part 2 of our webinar training sessions. We ran the previous one last month. And this webinar is titled Flexible Unground Granular Material Pavement Design, Field Characterization, Climatic Effects. And I'm Jayantha Kodikara, Director of the SPARC Hub. First, I would like to acknowledge our SPARC Hub partners. You can see on the left-hand side, our industry partners led by ARRB, Austroads, and CIMIC Group. On the right-hand side, we have our university partners, and then right-hand bottom, we have the industry partners. I would also like to acknowledge the contributions made to this webinar by IPWEA, City of Monash, and also our SPARC Hub colleagues who has helped me to put this webinar together. Dr. Aruran, who is the Hub Manager, Dr. Troy, one of the research fellows, Mr. Samira, Research Officer and PhD Scholar, and Chaturi, PhD Scholar. You can send your questions by clicking on a QA button. Please type in slide number and question. Questions will be answered anonymously. We also have put this webinar PDF files in our SPARC Hub YouTube channel, which is given on top. So first part of the webinar today is empirical, flexible, unbound granular material or UGM pavement design. As you know, unbound flexible materials constitute about 90% of Australian pavement system. And this flexible UGM pavement design approach is based on past work undertaken on airport pavement design, calculating the granular layer thickness over subgrades for different load levels. Then it was the experience with pavement performance that has culminated to this empirical approach. So this chart is very common for empirical flexible pavement design. You have on your x-axis the design traffic given in equivalent standard axles. On the right hand, on the y-axis, you have the thickness of the material or the cover you require for a certain subgrade. Subgrade is characterized by the CBR value, which we looked at last webinar. So for a certain CBR value, you can find the amount of cover you require to make up the pavement. So for example, if you had a CBR subgrade of 4 and equivalent standard axles of 2 million, 2 times 10 to the power 6, then how much cover you require on top of that can be determined by going to the CBR4 line, which is this line, and then reading off on the thickness of material required 480 millimeters in this instance. So that material can be a crush rock material, and it doesn't designate what is the quality of crush rock material, but typically crush rock has more than 30 CBR value. So if the CBR value is 10, for example, for the subgrade, then you can go to the CBR 10 and then read off the value, and it will be 300 millimeters. So of course, the CBR value you select for the subgrade is very important for the pavement thickness. If you estimate it to be 2, then you have to have 480 millimeters. If you estimate it to be 10, you will have 300 millimeters. So that make a big difference in cost and so on. So that gives us that the CBR characterization would be valuable thing to do for the climate and the type of pavement is being considered. In many instances, we look at sublayers. For example, base layer is divided into good quality crush rock on top and a sub-base layer with marginal level. So in this instance, we have a scenario where same design traffic, 2 million ESAs, and the subgrade is 4. So we have 480 cover, which is needed. But that cover can be broken up into 2 parts. So if you have marginal material with CBR 15, so you can go to 15 as the sub-base layer, and then this thickness 265 can be used for the sub-base layer of CBR 15. And what's above will be your crush rock layer, 215. So in summary, base layer of 215 and sub-base layer of 480 minus 215, 265. So that pavement is a 2-layer base system and over subgrade of 4. Certain road authorities, in this case, VicRoads is cited, have developed variations of this graph, allowing for local materials classifications. In the last webinar, we mentioned VicRoads has class 1 to class 4 crush rock types with various gradations. And here they are used in this fashion. Class 1 crush rock is the good quality crush rock considered above, and others are considered in this fashion. In addition, they also have a consideration for the climate in the pavement area. So rainfall is used in this instance for top 100 millimeters and remainder of the base. So if the rainfall is less than 500, and depending on the traffic level, if the traffic level is less than 1 million, you select 60 for this example. And if it is between more than 1 million and less than 7 million, then you select 80. When the rainfall increases, you have to have a higher subgrade value because effect of water will be more. So that's one way you can accommodate the climate effect into this design. So although this technique is very simple and commonly used, we have to be aware of the assumptions that are inherent to this empirical design. So this technique and the chart has been developed for certain conditions of field testing. So conditions that were present for the empirical data are applicable. So if we use it beyond that, then of course, we are extrapolating the results. So we know pavement distress is primarily due to rutting, considering both subgrade and granular bases together. When we have a thicker granular layer, the stress going to the subgrade may be very low, and therefore subgrade rutting may be limited. However, the crush rock layer can rut and produce surface deformations. So that must be taken into account. So when the granular material thickness varies, the potential for change in rutting is not considered in this empirical chart. So that need to be kept in mind. In addition, variation in climate is not considered in the chart itself unless you go to variations such as in VicRoads. So I'm trying to compare here this empirical design with the Austroads mechanistic design. Austroads mechanistic design, primarily using circular program, also can design the flexible pavements. So for example, on the right-hand side, you have a subgrade and the base, single base for this example, and standard axle with dual tires. So 80 kilonewton axle load. And with that loading, you get stresses in this pavement structure, and you can determine for a certain subgrade what is the required thickness, just like using that chart. However, when you use the mechanistic design, you need to designate a certain modulus value for the base. So you notice one thing, we are designating modulus values, not CBR. So typically, unless these values are measured in the lab, people convert the CBR of the subgrade into modulus by multiplying 10 times CBR in megapascals. So CBR 4 will give 40 megapascals. And then a base value is needed. So Austroads design guide has developed this criteria for pavement subgrade rutting. Actually, it is the overall rutting for the flexible pavements. So this formula tells if you have a certain vertical strain on the subgrade, here given near mu E due to this loading, then the tolerable number of cycles or equivalent standard axles is given here by this factor and this constant. So this is comparable to the chart. So chart and this result will give the same result provided you use EB 350 megapascals. So that's the standard base value you need to use to match with the chart. So that's how this equation for rutting has been developed for the mechanistic design method. So what about if you use base modulus other than the reference base modulus of 350? If you use reference, let's examine this example. For instance, from empirical chart for CBR4 and a design ESAs of 2 million, we got 480 in the previous chart example. If you put the same things into Circle and run it, and we select CBR for the subgrade is 10 times CBR, 10 times 4 is 40, and the base value is standard value, then cover thickness of 480 is determined after rounding off. So they are matching, right? But if we say I can run the same problem with EB 700 MPa, high quality crushed rock, then I would get 454 from Circle, 26 decrease. If I have 150 MPa, that is 15 CPR, then I'll get 540, an increase of 60. So these changes will not come from the chart. Chart will always tell 480. So you may need to be aware of that as well. So there is an apparent difference in the empirical design or Austroads mechanistic design method, as I explained. In addition, if you have two-layer system for the base and sub-base, you will have more changes. So for example, empirical design, we got for that example 265 and 215 for the sub-base and base. But if you go to mechanistic design, we have various options how to differentiate these two layers. In this example, we got 265 millimeters for the sub-base and 205 millimeters. You get the same life. Alternatively, we can select 215 for the base and 250 for the sub-base. So of course, this may be more economical. So that option is also there. The next is field characterization and QA/QC. So density and moisture measurement are commonly used as per field specifications. We discussed the field specifications for compaction in the last webinar. So density measurement is commonly used in field characterization, and nuclear density gauges or sand replacement is sometimes used, but nuclear density gauge measures the wet or bulk density. So wet bulk density is dry density times the 1 plus W. W is the water content. So in order to get dry density, which is normally the specified value, you need to determine water content as well, right? And water content, of course, may need oven drying and so on. So typically, specifications can involve a density ratio, which is field dry density. If you determine that using this formula, then you may have divided by maximum dry density for with Proctor, modified or standard, usually modified is used. Then a specification might say has to be more than 95%. So if dry density ratio is needed, then you need to determine all these things, and it can take some time. Sometimes it can potentially delay the construction. So this is a problem currently which happens in the field. I mentioned last time, degree of saturation or DOS is also a very important parameter which determines the pavement on UGM and soil pavement performance. So if DOS can be determined, if the water content and density are found, DOS can be found. But in the field, if you want to find DOS, you will have to use the nuclear gauge results. You have to find the bulk density, which is this. You also have to find the volumetric water content. That's what coming out of the nuclear gauge. Then you can use this formula to determine the degree of saturation right in the field. But determination of the moisture content from nuclear gauge may not be as accurate. However, it can be quite useful as done in QMR for their practice. Modulus and other measurements. So modulus is another way of looking at quality assurance. There has been this discussion going on lately. Can we even replace density measurement by modulus? So I'll discuss the modulus measurement also in some length. So modulus measurement in the field, we use surface-based impact devices, light falling weight deflectometer or LFWD is commonly used, Clegg hammer, GeoGauge, and other similar devices. They all calculate a certain force applied to the certain area of ground, which is compacted, and then also determine the amount of deflection which comes with that force. So force divided by the area gives you stress. Stress divided by deflection gives you some stiffness. So that can be used to some extent. Then other measurements include cone tip resistance measurements, Panda probe and dynamic cone penetrometer. So they are based on some penetration resistance. So some typical things to consider here, repeatability wise, these measurements are generally lower than for density. However, density is not very sensitive and values are very close to each other, whereas modulus varies quite a lot. So that may be some advantage as well, just like it can be a disadvantage. Testing duration is faster than for density. So you can do the testing quite fast and move on with the results. Different soil types, these techniques can differ in their application. And of course, modulus is a function of stress as well. Therefore, that needs to be considered. And cost can include initial and running costs. but they are comparable. So this work has been researched by NACO project in Queensland, and Lee et al., Lee, Bert, Luke, and Lazy. I think they had a quite extensive work done on this topic, and you can download their reports from their website for more details. Modulus versus stiffness. So this is something one needs to understand. Stiffness is a pressure or a force divided by deformation as measured by all these stiffness devices. So has the units of kilopascal or megapascal, some pressure divided by length, millimeter, or force divided by length, kilonewton by millimeter, or any other unit of that nature. So because of this millimeter or scale length here, it is normally scale dependent. That means it depends on the size of the loading area and the configuration. Sometimes symbol K is used for stiffness. So it is not really a material property, it's related, but it is a function of the loading configuration. But modulus, on the other hand, is a soil property, and it is defined by stress divided by strain. Therefore, it has units of megapascals or similar, some pressure units, and it is scale independent, right? So typically, when you perform a stiffness test in the field, it looks at the soil sampled area, how much is stressed, and using some back analysis technique, it determines the soil modulus. So that's the one normally one should report, not the stiffness. So then one should ask the question, which modulus? Modulus also depend on number of things. We mentioned the stress or the strain level exerted on the soil, whether it is loading or unloading. For example, look at this stress strain diagram for soil. When you start loading, the gradient gives you the modulus. Initial gradient is very high normally, and that's initial modulus. Then when soil starts to yield and become nonlinear, your modulus drops. So that's the modulus now, and it's normally referred to as secant modulus or loading modulus. And that will be this stress level divided by this strain level, right? But if you unload from this position, you will be going down in a path like this, and that's known as the unloading modulus. Because modulus is normally referred to elastic modulus, this unloading modulus is normally the correct modulus to use. Nonetheless, if you are using loading scenarios, then secant modulus is also reported. So we need to know which one we are dealing with. So this diagram here shows the secant modulus variation with strain level. So modulus on the y-axis, strain experienced by the soil on the x-axis. So very small strains happen when there is seismic kind of loading. So HS here is hammer-induced seismic loading. So you get high modulus there, applicable for earthquakes or dynamic loading and so on. But base, subbase, subgrade due to traffic loading usually strain in this region. So the testing we do with light falling weight deflectometer actually falls in this region, and that's actually comparable to the strains experienced by the pavement. So it is good. Then RMT, resilient modulus testing, that's normally undertaken in the laboratory for a modulus determination used in pavement design, is also in the similar range. So that's also good. CBR, for example, we mentioned in the last webinar that CBR is also kind of a modulus or relative modulus. So that modulus is actually straining soil a lot, 5-10 millimeters, 2.5 and 5 millimeters over a certain length. So that strain comes here, and that means we are likely to get a lower modulus by that method. Although we try to correlate that by multiply by 10 to this resilient modulus to be used in design. So that can be understood in that fashion. So modulus or density for QA. This question is also now being discussed in the scientific engineering community. Let's look at some issues. Resilient modulus, I am using the symbol ER, is commonly used in pavement design. So modulus is used in pavement design. That's a resilient modulus. But of course, the measurements we make in the field are different kinds of modulus because of those reasons we mentioned. But they are in the same basket. I mean, they are all apples, if you like. So modulus has similar characteristics. They may not be exactly the same, but they are similar. Field measured modulus may have better correlation with ER. So therefore, any measurement of modulus we do can have good correlation with ER normally. However, density, on the other hand, defines the void ratio, which defines how compact the soil is. So for example, this formula here, dry density, GS rho W, these are constants. Void ratio and dry density are directly related, inversely. Therefore, density basically defines how compact the soil is. But the high density limits the amount of rutting. Therefore, it gives main performance requirement for the unbound materials and soil. So it directly relates to rutting. So I'll explain that later, how that can happen. For most materials, modulus increases with density. So they are correlated together. When density goes up, modulus goes up, right? However, for compacted soils, modulus is a function of both density and moisture content, or degree of saturation, DOS. Because two variables are playing together for modulus, this dependency can give rise to unintuitive correlations depending on the data set used. For example, you can get a negative correlation. As the density goes up, modulus can drop, right? Which is unintuitive. So that can happen because of this dependency on two variables. Just to examine this a bit closer, let's look at this diagram. This diagram is for CBR, right? As molded CBR for lateritic gravel reported by David Toll in UK. So I have taken this data set and modified a little bit, and it's reported in one of my papers as well. So it's hard to get a good data set characterizing like this. So this is a good one. So let's look at that. Dry density against water content. So you see the green line is for Proctor, and then you have intermediate level compaction. Then you have heavy compaction, which is modified Proctor, right? So you have the three compaction curves, and you have the saturated line, and you have the line of optimums. So I mentioned earlier, very important when you plot your compaction curves to plot the saturated line as well as the line of optimums. Because this line of optimums is a very important line demarcating the change in behavior of compacted and UGM soils. So if you go to that side, you can expect problems. You can stay here or further away, you can normally reduce problems in cyclic loading, right? So we mentioned that last time, and I'll reinforce that this time as well. So what are these dotted lines? These dotted lines are contours of as molded CBR. So for example, if I go to 20 here, so if I compact a soil here to this density, let's say 22, and dry density is this value, 1.42, at this point, I will get CBR value of 20 as molded, not soaked, as molded. If I go to here at this moisture content and get this density, and I'll get 20 as well. So along this line, I'll get 20. Likewise, if I contour the common CBR values, I get this kind of graphs. So you can say they have a funny shape. So if I draw a small line here, in this region, they are going up actually like this, right? That's because the influence of capillarity or suction is diminishing, right? And in this region, influence of capillarity is increasing. Therefore, you get this curve this way. And past this optimum degree of saturation line, you tend to get very small values, right? You can also look at this right-hand side picture, CBR against water content. I'm just selecting a certain water content and I'm selecting change in water content and plotting CBR for different compaction curves, right? So for the heavy compaction or modified Proctor, you can see passing the optimum values, your values drop dramatically and eventually they coincide regardless of any density, you tend to get similar values. So that's the kind of complex behavior you get and the influence of the optimum degree of saturation. Now that's CBR, but if you go to any other stiffness measurement such as LFWD, we don't have results at this stage, but I am inferring results based on our experience. And you are seeing here is the contours of in the dry density moisture content frame. I have also drawn the line of optimums, and you can see these are the contours, likely contours of the modulus values, constant modulus values. I would think they all will have a similar trend for all modulus measurements. Of course, soil is variable, so you can get some differences, but generally speaking, this is the likely pattern. So in this pattern, if I pick some points here, these stars, and I plot the modulus against the dry density, I might end up with this whole thing. So there's no correlation everywhere. They're everywhere. But if I select a certain moisture content, like these red dots, I might see a positive correlation, E versus rho D, increase in density, increase in modulus. But if I shift this red vertical line to here, higher moisture content, I might get a negative correlation as I go towards this line of optimums. So that you can see that difficulty in these correlations. And that's because of this dependency of this modulus to two variables. So when something is dependent on two variables, if you try to plot it with one variable and how it plays out together in this variable space, you will get different values, right? That's the problem. So we need to take that into account. And we can replace the water content by degree of saturation and keep the density and replace that with void ratio if you like, if you want to be more technical. But we need two variables. Stress variation during traffic loading. So here, stress variation, if you have a certain position under the traffic, you see it's happening here. And when the wheel is right on top of it, your stresses will be maximum. So this is the vertical stress, it's maximum. And when the wheel is approaching, it's developing, and the wheel is going away, it's decreasing. Same thing will happen to horizontal stress, and it will also go like that. So if we get the difference, that's the deviatoric stress, it will go like that, right? Deviatoric. But if we get the mean stress together, then we get this kind of thing. So that's the one simulated in triaxial, if you like, RLT test. We cycle this kind of behavior. But one thing missing from triaxial to the field is this shear stress. The shear stress becomes peak when the vehicle is close to this point, but not right on top of it. Because of that, and it dropped down to zero right on top and then fades away with this lag. Because of this lag in the shear stress, you get stress rotation, right? So principal axis rotation takes place, and that can influence the rutting. Unfortunately, RLT cannot simulate that. So in many instances, this principal axis rotation has been found to be significantly increasing the rutting if it is not considered. So currently, SPARC Hub is working on this topic to develop a better test method, but it is not easy. Resilient modulus also depend on soil type, particle size, type, shape, plasticity, etc., and the stress level. Primarily the mean stress or the confining stress. So as you know, sand and other particulate systems, if you don't confine it, they will flow, right? They will not have any modulus, just like walking on dry sand, right? Your foot will sink, and eventually, when it confined, it will have modulus and it will resist movement. So that's what we are seeing here. But of course, you can see the degree of saturation changes: 30% high, 50%, 79%, 94%. So this is in the closer to the DOS optimum DOS, SRL. So you can see the drop, right? And more clearly here, modulus against DOS, and as DOS goes above the optimum values, you get values decreasing, and also they come together. These are equations from the USA design guide, which encapsulate such behavior. This is a field data set taken out of Lee et al. Report in NACO project for PRIMA FWD test for site 1. So you can see a modulus against density, they have a bit of a negative correlation, right? So I have also plotted the degree of saturation values estimated. And you can see these low values are all high degree of saturation, 97, 94, 98, 98. So you can even draw a line. So if you ignore that, you might even get a positive correlation. So there are more work to be done on that topic. Modulus against SR minus SR opt, you get a genuinely negative correlation, right? Because we expect that as this position is passed, values will drop. So there's another way of compaction control, which is known as continuous compaction control or intelligent compaction. This is another topic SPARC Hub is working on, and that is basically rollers, which has accelerometers and other sensing devices to determine the amount of compaction received by the soil, and indices like intelligent compaction value is found that those indices are also related to stiffness. So they will have the dependency on the density and moisture content, as I mentioned before. So sorting out those results which are coming out in this fashion need to be examined. And I'm not going to talk about this at length in this webinar. So next topic is rutting. So rutting is the performance criteria for UGM and subgrade materials. We discussed about rutting last time, and we can get shear-induced rutting or densification, volumetric densification. So when you have densification, we see this kind of shape. When shear, you can get heaving as well, but it could be a combination of the both. So let's look at how this rutting is handled by pavement design guides. So USA has a direct rutting calculation equation. So delta P is the rutting, and that same equation applies to unbound as well as subgrade. So you can calculate for unbound layer and subgrade layer and add them up to get the total rutting, which then is the performance limit. How they do that? They use this approach. They assume the vertical strain approach exerted on the subgrade or layer you are examining for rutting determines the amount of plastic deformation or rutting. So this is the elastic value or resilient value, and that determines the amount of rutting. So how do they do that? They need a scaling parameter. So this is the value calculated from the field pavement, elastic strain. They have a conversion factor. E naught is the rutting and ER is the resilient strain measured in the laboratory, right? When you do the RLT test, you can determine the amount of resilient strain and the corresponding plastic strain. So this ratio is the E naught over ER. So if you know that for this resilient elastic strain, you got this much rutting. In the field, I have this much vertical elastic strain, therefore amount of rutting is scaled, and the height and other factors and the number of cycles, they are incorporated in that fashion. Austroads approach, as I mentioned earlier, it is the empirical design guide directly correlated to a fatigue kind of formula with the vertical strain experienced by subgrade. But it doesn't have a calculation separately for rutting in unbound material and the subgrade. So rutting permanent deformation depends on all these factors. I think I mentioned that before, so I'll keep on going. So here, I showed this picture in my previous webinar, but I'll show it again. And what we have is the rutting or permanent deformation against number of cycles. So here we are showing the loading that happens in the field by traffic loading. So as the vertical loading goes up, shear stress is also going up. So if you come close to A, then we are loading heavily, B, intermediate, C, low level. So what is this red line? This red line is the Mohr-Coulomb envelope, which designates the strength of the material, unbound or subgrade. So if we come close, if we are far away from that red line, like C, amount of rutting is less and you're shaking down and you have a long life for the pavement without much deformation. That is a good scenario. If you come intermediate, you will have higher rutting, but failure can happen a little bit prematurely than the other one. But if you come very close to it, you will have lots of rutting and premature failure. So that's the one we may want to avoid. So this red line, if it is far away from this A, it is good. How it can be far away? Gradient is the friction angle, which is based on material. So 40 to 50 doesn't change a lot. Whereas cohesion is based on the density, how much void ratio you have achieved. So higher the density, this line will shift up. In addition, where's the moisture effect coming? So when you have decreasing degree of saturation or decreasing moisture content, this line will also move up. So moving away from this loading region and providing better performance, less rutting. That's how it works. But if you wet it, it can come down. If you have no compaction, it can come down and rut it altogether. So that's how density and moisture can help minimize rutting. So here, some example, permanent deformation, again, number of cycles using repeated load triaxial testing. So different load levels have been used, lower load level here, higher load level here, even higher here. So you can see degree of saturation 45 and 55, they haven't rut much at all, right? But when you go to 70%, and normally optimum is about 80% or higher, so they have rutted, right? Quite a bit, 78 has rutted a lot. So that shows that as you approach this optimum degree of saturation, you can expect rutting. So although compaction is, highest density can be achieved at the optimum level and minimum energy is required to do so in the field, performance-wise under cyclic loading, it is not the good position. You have to be lower degree of saturation. That's the reason why QMR, for example, allows dryback to about 70 and so on, or less than 70. So next part of webinar, I'm going to cover the climatic effects on unbound pavements. So this picture depicts ground-atmosphere interaction. So you can see the ground surface, and then you have at some depth the water table. This is the water table here. And you may have a capillary fringe as well, right? Depending on the soil type. And below the water table, your water pressure will increase with depth, as you know, and the soil is saturated. But above the water table, your water pressure will decrease or negative, or we call it suction, right? And it will be like this, straight line backwards, if the soil is covered. But if soil is partially covered like a pavement, where it can interact with the atmosphere, we can dry the soil during drying times, then the suction will increase. So we get profile like this for the water pressure or suction. When it is raining, it will drop back and you get this kind of green line. So this variation is the one which can lead to deformation, shrinking, swelling, and so on. And this zone is normally referred to as the reactive zone. So that's what happens with the ground interaction. So climate is, excuse me. Due, can you not shout? I'm doing a webinar. And sorry, doing things from home, complications, right? So soil and climate of Victoria. So here you can see the Victorian map, and the soil types are also given. Western side is basaltic terrain, right hand side is has Silurian materials and so on. These contours are Thornthwaite Moisture Index, TMI contours. They characterize the climate, and plus means higher the plus, more wetter the climate is. Negative, more negative is drier climate, as you can see in the middle. And when you go to the alpine region, you'll go to plus 100, lots of rain. And in Melbourne, it is around 40 here, and then eventually come to slightly negative towards the west, where it dries out. So these are typical classifications. So other side of the coin is the soil. Soil reactivity is also determined by the percentage of fines and how reactive the fines also. How reactive the fines are determined by plastic index. Higher the plastic index, the more reactive the fines are. But how much fines are there in the pavement material is also important. If you don't have much fines, then although PI is high altogether, it may not be effective. So you have to get this together. So this example shows what happens when you lay a pavement in the ground, and you have the thin seal or cover, if you like, surface, riding surface. And you also have the pavement material and the subgrade. And I'm picking 2 points here. Either one of them doesn't matter. So you can have this kind of scenario. When you have time 0, when you start your pavement, let's say you start from a fairly wet condition, wet of optimum or something like that. Then during time and soil dries out, and it can come to equilibrium kind of position with the climate, and equilibration will happen between these layers as well. And then in the long run, it will undergo wetting and drying depending on fluctuations in climate, more or less around the equilibrium. Unless climate is changing, this equilibrium position might also shift. If you start from a drying position, it will wet up to the equilibrium and then go up and down. So the equilibrium normally happens to suction, not the water content, because suction is the potential of the soil which it equilibrates, like temperature is the one which equilibrate when you have hot and cold materials. Suction is the one which will equilibrate. For example, at this interface, if you start with wet and dry, eventually suction will equilibrate, and that determines the amount of moisture in the 2 layers. So I'm trying to show you a simulation study we have done on a test flexible pavement, and it is from Dubbo, New South Wales, and climate normally 660 millimeters. And this was reported by Carteret 2015 in his PhD from Newcastle University. So we have got this data set, and my student Chaturi, I should say scholar, Chaturi has done the simulations as part of her PhD. She's about 1 year into her PhD. So preliminary calculations I'm showing you. So pavement is unbound crushed rock. We are treating these two layers similar as one material for simplicity. And then subgrade compacted layer and the uncompacted subgrade, right? So we are simulating single UGM subgrade and then so compacted subgrade and then normal subgrade. So these are the rainfall patterns and so on. So this diagram here is a result of the simulation and variation in degree of saturation with time for 2 years. And simulation parameters, some of the parameters are given here. I mentioned permeability. We should be aware that what permeability we refer to. Normally, when we say permeability, it is saturated permeability. So I haven't put the term saturated because that's a commonly reported one. Unsaturated is when soil dries out, what is the permeability? So seal permeability is 2 times 10 to the 5, which is fairly permeable. Base permeability is twice that, so that's also very permeable. Compacted subgrade is 10 to the minus 9, like clay. This is a little bit, because this compacted is lower, this is a little bit higher. Right? You know, clay liners normally have 10 to the minus 9, which is per second or lower. So here, this diagram, we have degree of saturation on y-axis, time on the x-axis. So 30 days, 60 days, 90 days, and so on, up to 2 years. So we are looking at top of the base layer green, middle of the base blue, and so on. So here you can see green, and also you can see the rainfall pattern in the light gray here. And when the rainfall spike happens, the top of the base layer responds to that and goes up and down, right? Goes up and down in this instance, right? And the red one is the bottom, and the light green one is the middle of the base. So they also follow together and goes up and down as well. So you can see actually the base and the middle have higher water or higher degree of saturation than the top, because water is flowing down quite quickly, right? Down because of the high permeability of seal and the base. So base get higher degree of saturation, and sometimes they reach full saturation during rainfall events. And this may last for several weeks because this axis is quite close to each other. You can see the blue line, which is top of the compacted subgrade. It has the highest water content. So because water has accumulated on the top of the compacted subgrade, right? But if it is compacted, then it has higher strength. So that may be a good thing. So that is the scenario you can get in more permeable seal and permeable base. So I am using DOS because I want to be staying away from this optimum DOS if I can. So certain regions I am exceeding that. So this is the compacted subgrade and below normal soil subgrade. So you can see what happens there is generally the top of the compacted subgrade responds to the water because it's receiving water from the base layers. But rest is pretty much equilibrating to a certain value. In this instance, somewhere around 0.8 or around that. So almost like optimum, right? So that's what happens in this instance. There's a reason for it. Unfortunately, I don't have time to explain that. It's due to the water retention curves and how the equilibrium suction is developed. But it gets high degree of saturation eventually. So subgrade may be vulnerable in this instance because it's giving more than it's approaching actually 0.9. So which is above the optimum values. So this is 10-year simulation of the same thing. So we just simulated 10 years, but you can see basically we repeated the climate. So climate is not accurate. So which is just repeated climate. After 2 years, same climate is put in for the rest of the time. But you can see once it reaches that equilibration, it's just fluctuating around there. Same thing in the bottom diagram for subgrade. This one is different. You have 2 times 10 to the minus 5 for the base seal, but next one is 10 to the minus 8. So we have reduced the seal permeability quite significantly. So good tight seal. Normally, good seals must have this kind of permeability, right? So whether we can maintain it for long term is the question, cracking and deterioration and so on. But let's say we maintained it. So this is a 2-year simulation. You can see all the values, including the top, they have gone down. So this is degree of saturation now has dropped to around 0.5, right? So it's a very good pavement. It will last very well. Degree of saturation wise, it's in that region where rutting and other things doesn't happen. Shakedown can be achieved, right? So you can see the importance of the seal. Then here, another example. Let's say seal is permeable because it cracks and other things, but base permeability has been dropped to a low value, 10 to the minus 9, right? This is not common. So let's say we do that. If we do that, then we can also bring down these degree of saturation variations. Red means bottom of the base. Light blue means middle of the base. So you can see they are very low, less than 0.5, right? So you can maintain for 10 years in this instance, pavement in good shape. But of course, this is not commonly done, right? But require more research, I think, in this instance. So here you can see a scenario where long term we done base permeability is increased and showing the results in the long term comparison for the subgrade. But subgrade likes to go back to that 0.8 again, regardless of base permeability has been reduced. That's because of that equilibration, right? Because of the water retention characteristics are different, and that's why it is doing that. But I think this analysis is not entirely accurate. Now I realize because we haven't changed the water retention curve for the both in a coupled way. Further analysis might be needed to get this result more accurate. So what are the take-home messages for from this webinar today? Empirical flexible pavement design gives consistent results with mechanistic design for 350 megapascal or CBR 35 base modulus. Any deviation from this standard can produce somewhat different results from empirical to mechanistic. Any variations in thicknesses from standard may also result in differing rutting and climatic effects. So some of the variations possibilities I explained. Modulus is a function of both density and moisture content or degree of saturation. This can result in unintuitive, such as negative correlations, when plotted one parameter, such as density. Ideally, we need all these 3 parameters to develop specifications, but more targeted research is needed to come up with innovative and practical specifications. So we are currently working on this topic. Rutting can be reduced with cohesion imparted to UGMs and soils, with the apparent cohesion imparted by the decrease of degree of saturation, or more precisely, increase of suction. Rutting can increase markedly depending on stress, as DOS goes beyond 70% or so, approaching optimum DOS. So I have been maintaining this DOS as an important parameter during these webinars. Maintaining a low permeable seal is paramount for maintaining low DOS in UGMs. If UGM permeability is reduced, similar effect may be achieved based on the preliminary simulations I showed, but more research is needed. Unsaturated soil hydraulic modeling with climate simulation can be developed to examine climatic effects and produce cheaper and effective pavements optimizing to the climate. I mentioned CBR is double, you reduce a lot of cost. So with the climate in different parts of Australia, especially in dry areas, our rainfall has reduced. This may be important. And Chaturi's work can help this direction of research, as I showed you with the simulations. So thank you very much for your patience and listening. These references are there, so if you want to follow up further, and if you have an issue with downloading them, please contact us. We will try to send it to you. So now is the time for questions. Thank you very much.
So Jayantha, there's a few questions listed in the Q&A. Are you able to view that, or would you like me to read that out?
I should be able. Just let me just get myself a little bit organized here. There's a pointer. Oh no, not this pointer. And then Q&A. Yeah, just let me just read. So we have how can we differentiate thickness of different pavement layers during field modular determination by any method such as LFWD or DCP? That's a very good question, because most of these methods don't differentiate, because the back calculation methods has only allowed for a single layer. So only thing you can do is if you have a certain device, how much volume, what depth is contributing to that measurement. So LFWD, something like 300, 400. So that may be looking at the layer you are looking at. So therefore, that technique you select need to allow for the layer you are trying to characterize. If you are using, for example, IC with rollers, they can go to a meter or more, and therefore they will have the effect of the underlying layers. Unless you develop more advanced methods with multiple layer backfigure calculation, like done in falling weight deflectometers, then you have to rely on the method, how much depth is sampled by the device. DCP, on the other hand, is a different device. It's a cone penetrometer. So it does, cone resistance is the one which is coming mostly. So it samples where it is passing through, and that region is the one which is more important. Next question is slide number 22. So let me go to slide number 22. Slide number 22. The question
so Jayantha,
is,
that might have been related to the question above, I think.
Yes. Okay. Slide number 22. Yes. And then there's another question regarding climatic effects. Only rainfall is considered, which can be accumulated by soak CBR. It can be considered accumulated by soak CBR. There may be effect of temperature on the rutting of road surface as well as on road performance, isn't it? Well, in unbound granular materials, dominant factor of climate is the moisture. Of course, people might say moisture for those materials, that's the most dominant factor, for unbound materials, subgrade and the UGMs. Temperature has no significant impact, although it can influence the vapor pressure moment. But in our simulations, which we showed you, they are isothermal simulations. That means assuming a certain temperature, average temperature. We have also considered under such condition moisture flow equation as well as the vapor flow equation. So both vapor flow and moisture are considered in the simulation, but at a constant temperature. You can add the thermal effects into it, but of course that complicates the equation. But I think for UGMs, that effect will be very limited. However, if you go to asphalt, the situation reverses altogether. You will have asphalt dependent primarily on temperature, and moisture has a less effect. So if you want to simplify and capture essential physics rather than complicating your equations and making life difficult, unnecessarily difficult, we can probably use moisture for UGMs and subgrade temperature for asphalt. However, more research is underway on this topic. Then we have another question. Is there any research has been undertaken to how concrete waste used for Australian road pavement? Yes, our SPARC Hub member in Swinburne University has undertaken quite a lot of research. Professor J. Sanjay, who is a concrete expert, and he currently is working on geopolymer concrete as well, which is alternative to traditional Portland cement concrete. And then Professor Aruna Raja also has done quite significant work there in Swinburne. So yes, there's research done. So I will direct you to look into their work. And if you need assistance, please contact us and we will put you in touch with them. Next question, how does simulation have been done with the rainfall variation? I think I explained that to some extent already. Richard's equation is the moisture movement equation. Then we have a vapor flow equation based on diffusion. It is Fick's law. So Darcy's law encapsulated in Richard's equation for unsaturated soils, and the Fick's law, nonlinear Fick's law, is encapsulated in the other equation for vapor, are combined together with the moisture storage coming from the water retention curve to simulate the variations when the rainfall is happening and the evaporation is happening when the rainfall is not there, and the runoff is happening during rainfall. And all these factors are taken into account along with the bottom boundary condition, which is the water table and the capillary effects. So all those physics are incorporated in the simulations, and daily simulations are run to accumulate the water balance. So next question is, if we plot modulus against density instead of dry density, instead we see a positive correlation. No, we sorry, because I think dry density is normally used, but you are telling bulk density, right? The normal density is bulk density. Just a shifting of, if you plot the curve, like a compaction curve, normally it is plotted with dry density against moisture content, right? So you get a inverted parabolic shape. If you plot instead bulk density against water content, you get a slight shift of the curve to the left. I think left, yeah. But it won't make a big difference. The difference in this negative correlation comes because, if you want, I can explain. Let's have time. Yes, I think we have time. So how do I explain? So let me show here. I think you can see this diagram, right? So here I'm drawing dry density, or rho d, that symbol is better, with water content. And you have, I always tell that constant saturated line should be drawn, optimum line should be drawn. So that must be done. Normally they are not drawn when compaction curve is drawn. When you draw them, you will notice that whether your compaction results are right also. So it's good practice to draw them. So this is the compaction curve. And now if I try to draw on this, the modulus curve may look like this, like that. So modulus will peak away from this, this line. So during this region, if I try to correlate modulus and density, see, density is going down, modulus is going up. So you get a negative correlation, right? Modulus is going up, density is going down. So you get, when you plot modulus and density, you get a negative correlation. But here, this region, density is going down, modulus is going down, you get a positive correlation. Here, in the out of this region, you might even get a positive correlation, both are going down. But of course, things can change, but generally speaking, this is the problem. So this issue is playing out a fairly complex manner, but we can sort it out, but more research is required. Any next question? There are more questions. If we plot, okay, we dealt with that. The rutting performance criteria using Austroads is purely empirical and have no relation to material characterization, such as modulus of elasticity. Is there any work done to improve this criteria? Yes, it is based on that empirical design chart and matching that with 350 MPa base reference modulus and running the mechanistic model and developing that rutting criteria. So it is basically replicating the empirical design. Of course, empirical design is based on experience, and people have been happy with that. People have been happy with it. Of course, there's scope to improve. So we are working on that in the SPARC Hub at the moment. However, research to practice requires quite a lot of effort. So we are working with ARRB researchers together, and hopefully we can come up with something useful. So I think that basically is the end of questions at the moment.
All right. Look, I'd like to close the session. Thank you for everyone who put the answers through, but particularly thank you, Jayantha, for your presentation. In your takeaway messages, some of the keywords I think for me at a higher level is the fact that if you do it right, it's cheaper and more effective. And given, as I mentioned at a previous presentation, that given the amount of pavement we have in Australia and in the world, any degree of improvement makes a huge difference, funding-wise, money-wise. So, pretty important work that you're doing, and pretty important work to share, I guess. Certainly, the SPARC Hub will give us some opportunities to improve some of this knowledge too, which is great. So thank you, Jayantha. And thank you, Aruran, Kanchana, and David Hallett from IPWEA for supporting this presentation and their part in bringing it together as well. So very successful from my viewpoint, given the number of people that attended. So I'd just like to thank you all. And if you can just Jayantha, take away that you're making a huge difference. Thank you.
Thank you very much for everybody participating, and thank you, Ossie, for your kind words. Have a great remainder of the day.
Thank you. Cheers, everyone.
Bye-bye.